example, remember the inheritance example we did back in 5.1? Okay, and I want to explain to you how we can relate that to a definite integral problem. All right. Do I look good? All right. Okay. Old example, 5.1. Okay. Next time you see me, I'm from the Hunger Games. All right. I inherit $1,000. Okay. I inherit $1,000. Okay. I'm just repeating. I'm repeating the same setup we had when we started chapter 5. All right. My same spending rate. All right. After T years. Right. And this is always changing. It's non-constant. After T years, I spend at the rate of $10T per year. Okay. So, for example, well, I'm accelerating my spending. After 1 year, I'm spending at $10 per year. After 2 years, $20 per year. After 2.5 years, $25 per year. So my rate of spending is always changing over time. All right, until I run out of money, which is about 14 years. I'm really stretching that out. All right. When you see rate, you're thinking what word? Derivative. You're thinking derivative. Okay. Although here, the idea is that you're basically being given information about a derivative, and you're going to do what I word. You're going to integrate it. All right, and that's going to be a key thing. Now, when we did this in 5.1, we used an indefinite integral to model a function first, the amount we had remaining. You could also model it as the amount spent. All right. But you can also think of it in terms of a definite integral. We're going to link these two together. All right. First of all, let's review how we would have done it back in 5.1. How would we have done it back in 5.1? All right. And I'm going to ask a different question, actually. Before I ask, how long was it until we ran out of money? The question I'm going to ask now is, how much do I spend? How much do I spend from T equals 5 to T equals 6 years? Okay. After the inheritance. All right. How much do I spend from T equals 5 to T equals 6 years? So between the 5-year mark and the 6-year mark. Right. Okay, so that's within the 6th year, right? Because the 0 to 1 is within the 1st year. So from 5 to 6, it's within the 6th year. All right. Okay, so how much do I spend? Question mark. All right. Now, first of all, I'm going to show you how you would have done this back in 5.1 without definite intervals. How would you do this using indefinite intervals? All right, so the old 5.1 method. Okay, the old 5.1 method. How do we do this? Okay, now, even though I'm talking spending here, I'm going to model an amount remaining. Okay, let f of t equal the amount of money in dollars remaining after t years. Okay, so it's the amount of money remaining out of my inheritance. All right, just to make this point, okay? Then that means that f prime of t is going to be what? I'm giving you the rate of change, but be careful. What is the derivative here? It's not 10t, it's what? Negative 10t. Why is it negative 10t? Because we're spending, and the function is being modeled as the amount you have remaining. Now again, you could have another function, g of t, let's say. That's the amount spent. Okay. But here, I'm kind of pointing out this trick. Be careful. Okay. I want to frame it like this to remind you, hey, sometimes we do want a negative sign. All right. If you're spending, the amount you have is declining. All right. All right. And we have an initial condition. We're going to solve this differential equation, right? We're going to solve this differential equation subject to, or such that, okay, what's the initial condition here? I inherit $1,000. Parse that using notation. What of what is what?
F of 0 equals 1,000.
That's right. F of 0 is 1,000. Right. F of 0 is 1,000. Okay. If you want, you can stick the unit here, right? This is dollars. This year would be dollars per year. Okay. All right, if you want to be a stickler, all right. Okay, we're going to solve that DiffyQ subject to or such that that initial condition is true. It's a first order differential equation. We typically only need one initial condition. All right. Folks, we did this back in 5.1. All right, so I'm not going to repeat all that work, right? So again, look back at your 5.1 notes. All right. What do? We integrated both sides with respect to t, okay, and we got a plus c over there, right? That helped us out with the plus c part. Okay, back in 5.1, we found that little f of t, okay, was given by negative 5t squared plus 1,000. Okay, or if you wish, 1,000 minus 5t squared. Okay, remember, that's the function that models the amount of money we have remaining after t years, at least until we run out of money. Okay, that domain issue we talked about last month. It took us about 14 years. All right. So now let's talk about this. Okay. If we were to graph this function, y equals f of t, what's the graph of that? Parabola opening which way? Down. All right. So here's t. Here's y equals f of t. All right. The y-intercept is 1,000. F of 0 is 1,000. Okay. Of course, the model is irrelevant over here, right? Negative values for t make no sense here. Okay. And again, my spending is accelerating with time. All right. And then it stops here unless I'm willing to go to debt. All right. So I want this piece of the parabola. Okay. Maybe it extends. It doesn't matter. But I want at least that piece of the parabola. Okay. Now, what's the deal? Now, this is not to scale. Remember, we found out that this year was about 14 years. Okay. This is not to scale, but okay. Now, here's t equals 5. Here's t equals 6. Not to scale. All right. So that here, the function value, the y coordinate here, is the amount you have left in your account at t equals 5. This is the amount in your account at t equals 6. So what gives me the amount that I've spent is basically the difference here, right? Okay, we're going down by how much? The amount in our account is drained by how much? Okay, and that basically gives you the answer, right? This drop. Okay, so this corresponds to the answer. Okay, how much have I spent to get from here down to here? All right. Okay, well, if we know this this function that models the amount we have in our account, that's our account statement basically. What do? Well, the answer is going to be f of 6, the amount of money we have at time 6, what? Minus f of 5, right? It's like you take your bank statement. It's your bank statement at time t equals 6. You subtract off, remember, it's always new minus old, right? Change is new minus old, right? So it's your bank statement at time t equals 6 minus your bank statement at time t equals 5, right? It's new minus old. Okay. And then how would we compute this? All right. Again, this is the change in your money, right? The change in your dollar amount, the change in your money. Okay. And how do we compute this? All right. Bracket. Okay. Well, we plug in 6, right? We have negative 5 times 6 squared plus 1,000. All right. Minus brackets. Don't forget your brackets here. Okay. Whenever you're subtracting something with more than one term, don't forget your grouping symbols. What do you do here? We'll look at 5. So let me reiterate what we're doing. We're taking this antiderivative, we're plugging in 6, we're plugging in 5, subtract the results, right? We're going to do this a lot. Okay. Now what happens if we work this out? We're going to get negative 5 times 6 squared plus 1,000, okay, plus 5 times 5 squared. Now this is very interesting. What's next? Minus 1,000. And what can I do here? Yeah, this is very nice. But we should have expected this. Okay, why is that? I'm giving you the spending rate. Okay. Now, do you agree that regardless of what you inherited, whether it's $1,000, $10,000, $100,000, as long as you haven't spent it in 6 years, right? Whatever you inherited, $1,000, $10,000, $100,000, okay? If I give you the spending rate, you agree that the amount that you spend, okay, is going to be the same regardless of how much you inherited, right? Okay? If I give you the spending rate, right, then you're going to have the same amount of spending regardless of how much you inherited, right? Okay? Because these are two kind of separate issues, right? strategizing, that's your finances, that's different, but, okay? But if I give you the spending rate, right, the rate of change, or the rate of change of your account, right, then this is negative 10t, okay, you agree. You will have spent a certain amount of money regardless of the initial condition. Bottom line, I know we talked about solving for C last time. In the end, if you're answering this kind of problem, did C matter? No, that's the bottom line. C is not going to matter. And a big smile should appear on your face. Okay? Because you're not going to have to worry about C when you do definite integrals. Okay? That's a key theme. Don't worry about C. The C is irrelevant. You may as well have taken the antiderivative where this was 0. Okay? May as well. That's an important point. By the way, when you work this out, you know, you get negative 55. How come this is negative? Because you spent it, right? So what does it mean? You spent. I spent $55. Okay. From t equals 5 to 5 to t equals 6 years. All right. So I spent $55. Based on that rate, I mean, that rate is sufficient. I didn't need the initial condition. That rate statement is sufficient. Okay. All right. I spent $55. Questions? You could have answered this question solely using 5.1 method. But don't you agree that this seems like too much work, right? You agree that we might be able to streamline this, right? Make it more efficient. Let's do it. And we can do it using a definite integral. All right. First of all, we're going to employ a shift in notation. Okay, there's a notation shift. All right. So we go from 5.1 to 5.6. Okay, there's a shift in notation. All right. Now before, in 5.1, okay, the idea is that you're given f prime, all right, and then you're trying to find out something about f. Okay, you're given f prime, and you're trying to find out something about f. Okay. Now in 5.6. Okay, the thing you're given as your integrand, we like to call f, right? F is your integrand, all right? And then the antiderivative corresponds to capital F, all right? So with the 5.1 method, we were going from little f prime to little f. In 5.6, we're going from little f to big F. Okay, so we're kind of shifting over the notations by 1. It's like, you know, here's f, it's like, you know, grandpa, pa, and you, right? There's little f prime, there's little f, there's big F. We're kind of shifting things over notation-wise. Okay. The idea is that this typically corresponds to the integrand. This corresponds to the integrand. All right. It's like the thing you're given. All right. So now, here's how we're going to model it using 5.6. Let f of t, all right, this is going to be the rate. Let f of t be negative 10t. Dollars per year. Okay, that's the rate, right? The rate at which your account, the rate at which your account is changing. The rate at which your account is changing. Okay. And implicitly, if you want to, you know, maybe write it. Oh, well, we write it here. Okay. Big F of t, okay, is the amount in your account. The amount remaining after t years. The amount remaining after t years. So big F of t here takes on the role of little f of t over there. All right. We're giving you little f of t, which is negative 10t dollars per year. This gives you the rate of change of big F. All right. So what's the idea here? What principle are we going to appeal to here? All right. Okay, here's sort of a side example. Let's say that we're graphing velocity against time. Let's say you're driving a car. You drive your car at a constant rate of 50 miles per hour. By the way, this is not my notes, so you might want to jot this down just as an explanation. You're driving your car at 50 miles per hour. You drive for 2 hours. How much does your position change by? How much have you traveled? 50 miles per hour, 2 hours, 100 miles. That's the area. You all agree? That's the change in this guy's antiderivative, right? This represents the change in S of t, the change in your position, right? If you're going due north on a freeway, right? You're going 50 miles per hour for 2 hours, right? You're going 50 miles per hour for 2 hours, okay? Then your position is changing by 100 miles, okay? So what's the idea here? If you integrate a rate function, you're getting the accumulated change in its antiderivative, okay? That's the basic idea. I'll state that when I draw this out. So what's going on here? We're integrating a rate function. Okay, so here, we're integrating a rate function. There's a reason why I'm raising this up. T and little f of t. Little f of t is negative 10t. How do you graph y equals negative 10t? What is that? It's a line, and it's sloping downward. Okay, different scales here. All right, what's a line sloping downward? Right. So here's the rate function. All right. Here's t equals 5. Here's t equals 6. All right. T equals 5. T equals 6. Look at this sort of trapezoidal strip here. Look at this strip here. Okay. What is that strip? That strip basically gives us the answer. Okay. This represents the sort of net or accumulated change in the big daddy F, in big F of t. And this effectively gives us our answer. It effectively gives us our answer. Okay? Once again, when you integrate a rate function, you're getting the accumulated change in the big daddy. Similar to this example over here. All right? And of course, this region is below the t-axis. That indicates that our answer is negative. That indicates that we're decreasing, or our account is decreasing. All right, questions? Question. How do we indicate signed areas in calculus? We use how do we indicate a signed area? An interval. What kind of interval? A definite interval with numbers. Those are the limits of integration, 5 and 6. Let's do it. So how would you solve this problem in 5-6, practically speaking? All right. Let's evaluate the following definite intervals. Evaluate means, simplify, find the answer. The definite interval from 5 to 6 of f of t dt. By the way, these better be t values. Okay, the limits of integration have to correspond to this variable. When we do u subs, that's going to be a huge issue. We'll talk about that. All right. Bottom line, we want to evaluate this. You agree this will basically give us the answer. Leave it to negative. Okay. Let's do it. So what are the steps? How do we evaluate this definite interval? All right. Now, when we did the 5-1 method, what did we do? You got the rate function, and what did you do to do it? What did you do to it? You integrated it, right? Okay. So your first step is to find an antiderivative. Okay. So, okay. First of all, let me write this out. 5 to 6, negative 10t dt. First off, I'm writing out what little f of t is. All right. Now here, I'll make some comments here. All right. You want to find an antiderivative. Okay, find an antiderivative. Okay. And we normally put that in brackets. All right. Well, the negative t pops out. Integrate t to the first. What do we get? T squared over 2. Going from 5 to 6. We know, and we put the limits of integration to the right of these brackets. All right. This is negative 5 t squared. 5 to 6. Wait a minute. You'll notice that I didn't write what? Plus c. Did I need them? No, because it's going to end up canceling himself out anyway. Where you have plus c and minus c, whatever c is. Okay. So, you know what? I think I'm actually going to switch my 2 and 3, but, well, why not? You don't need the plus c. You don't need the plus c, because again, whatever c is, it's going to end up being canceled out anyway. All right, that's my number 3 comment. All right. Now my number 2 comment. All right. Remember what we did before. Look, mechanically speaking, what did we do? We took the antiderivative. We didn't need the constant of integration. All right. And what did we do? We plugged in the 6. We plugged in the 5, and what did we do with the results? subtracted them. Right. Okay. So the answer is given by, okay, the answer is given, okay, big F of 6 minus big F of 5. Remember, the antiderivative is big F. Okay, the antiderivative is big F. All right? Big F of 6 minus big F of 5. All right, so here's what we do. We plug in 5. Okay, negative 5 times 6. I'm sorry, 6. 6. Negative 5 times 6 squared. These numbers can't go together. Sorry. Okay. Negative 5 times 6 squared. Okay, minus, and then what do we do? Plug in 5. Guess what? Well, we've seen this before, right? When you work this out, you're going to get negative 55. The interpretation of the negative sign being that the accumulated change is negative because we're spending, right? Our amount in the account is going down. So once again, I spend $55. I spent $55, between time t equals 5 and t equals 6 years. All right. Do you buy that? Do you buy that? The plus didn't matter. That should make you happy. So what is FTC? Okay, issue B. What is the FTC? Technically, this is FTC Part 2. Part 1 we'll mention later. Even though Part 1 is used to prove Part 2, Part 1 isn't as interesting, but I will mention it at the end. He's worth a mention. He could appear on your test, right? But Part 2 is by far the most important. So much like Star Trek, it's Part 2 that we like to focus on, more so than Part 1. Okay. And Godfather. Okay. This is very short. This is the shortest one of all. I told you about the fundamental theorem of arithmetic and algebra. FTC Part 2. This is the shortest one of all. Here's what it says. Again, we're assuming continuity, right? We're assuming continuity. The integral from a to b of x dx equals, all right, what do? We find an antiderivative for little f. Guess what? That's 5, 1, and 5, 2, right? You're doing an indefinite integral. Okay, this is an antiderivative. Okay, use 5, 1, and 5, 2 to get it. So using instructions 5, 1, and 5, 2, find an antiderivative. As you might suspect, this is the hardest part of the problem. All right? The rest is really trivial. Okay? From A to B. And what is this? What does this mean? Well, you plug in B, you plug in A, subtract the results. Bottom line, this is that. In a way, it's the shortest theorem of all. If you have continuity, the integral from A to B, f of x dx, is cap f of B minus cap f of A. Where cap f is an antiderivative. The plus doesn't matter. Any questions?
Lowercase f?
These are lower. Okay, no, this is lowercase. These are uppercase. These are antiderivatives. You plug into the antiderivative, the negative pi t squared. You plug into the antiderivative. Please remember that. No mistake. Okay, don't plug into the integrand. Plug into the antiderivative. Okay, that's the guy in the brackets. And that's what this means. Cap f of b minus cap f of a. Remember, you evaluate at the upper limit, minus, and then evaluate at the lower limit. Okay, new minus old. Okay, I know that we say the integral from a to b, but you plug in b first. I know that's confusing. You integrate from a to b, but you plug in b first. In a way, the way it's written kind of hints at that. Okay, we say it's the integral from a to b. This does kind of hint that b gets plugged in first, though. And by the way, this is the case even if b is less than a. If you're integrating from 5 to 3, fine. 3 goes here, 5 goes there. Fine. So this works even if b is less than a. Even if b is less than a. Still works. Questions? Questions? The proof is in the standard textbook. All right, now let's evaluate this thing. All right. Let's evaluate definite integrals. So why was it that name was 32, for example? Right? All right, example. And you're going to do a bunch of these, trust me. All right. Evaluate the following. The algebra here is going to get people. Evaluate the definite integral from 1 to 2. Fine. X to the 5th plus 7. For x to the 3rd is non-negative on that interval, and it's from lesser to greater, you can interpret this as an area problem directly. First of all, observe that this is continuous on the interval. Okay, in this class, that goes without saying. Okay, because the FTC requires that. All right. So we have continuity, good. We can apply the FTC. The question is, can we find an antiderivative? That's the hard part. Can we find an antiderivative? I hope you can. Hey, if you don't, we try to approximate this using what? Using whose sums? Riemann sums, yeah. See? So I give you some hideous thing, you can't work the algebra out, try Riemann sum. All right, but that's for an approximation, that will give you the exact answer. All right, algebra. What do you think? Break it. What do you think I mean by break it? Split it. Yeah. With two parentheses, x to the fifth plus x to the third plus 7 over x to the third all dx. You can do that if the plus sign's up there. You can't do it if the plus sign's down there. But you can split to the numerator. All right? Questions? Let's simplify this. Questions? Integral 1 to 2. What's x to the fifth over x to the third? X to the second plus 7 times. All right. 1 over x to the third. I'm going to want to write that in a power form. X to the negative 3 dx. I prefer this when we apply the power rule for integration. So you see, for the time being, we're doing an indefinite interval, right? It's like we're doing an indefinite interval. These limits will come in later on. We're still tagging along. All right. Equals, we're ready to actually integrate. Okay, I like to put brackets here. All right, from 1 to 2. All right. Okay, integrate. X to the second. X to the third over 3 plus 7 times. Careful. Integrate x to the negative 3. X to the what? Negative 2. You're adding 1. Over negative 2. Remember, you're adding 1. Don't think about, are you going away or closer to 0? It's add 1. All right? You add 1. I don't care if we're getting closer to 0. All right. Let's clean this up a bit. All right. X cubed over 3. Okay, how about minus fraction? All right. The 7 is on top. Okay. 2 is on the bottom. Who else can go on the bottom? X squared. All right. From 1 to 2. Remember, you got to plug these numbers in, so it's to your benefit to make this kind of nice. All right. X cubed over 3 minus 7 over 2x squared. That's an antiderivative. Do I need the plus c? No, I don't. It's not wrong, but just avoid it. It's just confusing. All right. From 1 to 2. All right. So this is my big F of x. You don't have to write this, but that is my antiderivative where c is 0. All right. Let's continue applying the FTC. We found an antiderivative, a cap F. What do I do now? Cap F of 2. What do I do? Plug in 2. Okay, I'll put it in brackets for good measure. 2 cubed over 3 minus 7 over 2 times 2 squared. Okay? Minus, don't forget your brackets. What do I do here? Plug in 1. That's cap F of 1. Okay, you don't have to write this. If it helps, fine, but you don't have to write these. Write these, though. Okay? Partial credit. 1 cubed over 3 minus 7 over 2 times 1 squared. Conceptually, it's not that bad. The hardest part is find an antiderivative. And then it's just be careful. Plug in B, plug in A, subtract the results. Remember grouping symbols. All right? I trust you to do that. Let me check to make sure this is correct. Okay, when you work this out, you get the magic fraction of 119 over 24. All right, great. Okay, question? The arrows are there. You don't have to write those. Those are reminders to you to put those brackets. Because a lot of people forget them, and they blow a sign. You don't want to blow a sign. Okay. You really should use them if you're subtracting something with more than one term. Anything else? Anything else? Yeah.
I understand everything you're doing. I'm just, for some reason, having a hard time relating this back to, like, little f and f prime.
Okay, this is little f of x. I'm basically giving you the integram, right? When I give you a problem like this, you're given the integram. And in the new 5-6 notation, we call this guy little f of x. He represents a radian, right? This little f of x. In the process, when you work indefinite integral, basically, you're finding big F of x, an antiderivative. Now bear in mind, when you work these problems out, whether you call them little f, big F, you know what? It doesn't really matter when you're working a problem. Just be consistent. I don't object. If you want to call him little f prime, then call him little f. That's fine.
Okay, it's just notation.
Yeah, it's just notation. Be aware that sometimes the book or I might shift. Instead of f and f prime, we might have big F and little f. Okay. Just be aware of that shift in notation. If you read a book or physics. Okay, but when you work with these problems, it doesn't really matter. Find an antiderivative. I don't care what you call it. Yeah. Okay, and then plug into the antiderivative. Okay, you know what? A lot of people forget to integrate. They forget to find an antiderivative. They're so relieved that they get a nice form, and then they start plugging numbers. No, you got to integrate. Okay, maybe we should do that. Integrate. Put two big arrows here. Integrate. You actually do want to integrate. Okay, so you can see here, this is the step where basically you're doing an indefinite integration, right? When you find an antiderivative, you're basically doing an indefinite integral, except you don't need the plus c. Okay, so that's how 5.1 and 5.2 get wrapped into this. Here, 5.1. All right. Questions? Questions? Symmetry is your friend. Okay, I know you are sometimes irritated when I keep asking you, is this even, is this odd? But that can help you work out problems. In count 3, you can work out 2 triple integrals instead of 4. Trust me, this is a good thing. All right, you like symmetry. All right, example. Evaluate. We're going to evaluate. Integral, negative pi to pi. And you might be smelling something here. Integral, negative pi to pi of x squared plus cosine of x dx. We have more than one term with grouping symbols, right? Okay. This here, little f of x, he is what? Even, right? If you replace x with his opposite, he doesn't care. Same value, right? This is even. Okay. Now, what does that mean? It means that, now you don't have to graph this, right? But if you were to graph this, the graph will be symmetrical about the what? The y-axis, yeah. Now, again, you have to do this, right? But it turns out the graph looks like this. It is like a smiley face, on that interval at least. Okay. From negative pi to pi. All right. And this will be non-negative also, all right? So in fact, the value of that definite integral will in fact be the region, the area of the region from here to here, all right? Now, here's the thing. When we do the FTC, at some point, we're going to need to plug in negative pi, at least as it stands. Now, you agree that we are very nervous about plugging in negative pi. Wouldn't you agree? That makes us a little nervous. Well, how can I rewrite this problem? Instead of integrating from negative pi to pi, why not integrate from what to pi? How about 0? Okay, take this area and do what? Double down. You agree that'll work. If we have symmetry, this will work. And you agree that plugging in 0 is usually more comforting than plugging in negative pi. I would agree with that. All right? So what's the deal here? We're going to write this as twice the integral from 0 to pi, okay, of the same, x squared plus cosine x dx. Okay, define symmetry. Okay. Bear in mind, this trick works if these are opposites. Right? If that were like negative 2 pi, then this trick would not work. All right. Well, let's go ahead. So quickly, let's go on. All right. We have the 2. Don't forget the 2. All right. Big brackets. All right. From 0 to pi. Okay. Integrate x squared. X cubed over 3. Okay. Careful, folks. Whose derivative is cosine x? Plus. Check. Guess and check. Whose derivative is cosine x? Sine of x. Focus on the derivatives. Come on, man. Like I said, I'd rather have you memorize 6 than 12. Focus on the derivatives. If you try to memorize the integrals also, I think there'll be math confusion. Focus on the derivatives. All right. 2 big parentheses. We might need them. All right. We might. Okay. The 2 applies to everything. What do I do? Plug in what? Pi. Plug in pi first. Pi cubed over 3 plus sine of pi. Minus, and then do what? 0. Plug in 0. Wait a minute. If you plug in 0, what do we get? 0. Yeah, you can see quickly, we're going to get but still check it, right? Oh, and by the way, what's sine of pi? Hey, that's 0 also. Hey, I love this. 2 pi cubed over 3. Beautiful. 2 pi cubed over 3. You get lovely results. All right, 2 pi cubed over 3. And the area here is 2 pi cubed over 3, what, square units? Maybe square meters if they're in meters, right? Whereas if we had plugged in negative pi, you might be scratching your heads a bit. Right. Yeah.
On the test, just when, since this all is coming together, are you going to have us just find the antiderivative of something? Are you going to say use a u sub on it, or are you just going to have to look at it and think to ourselves?
You should be prepared to recognize when you need to use that.
Okay.
Yeah. That's a skill you need to develop. Yeah. A good point. You'll need to know when you need to do a use up. And by the way, we're going to do that in just a moment. In fact, I would say that's one of the problems that a lot of people fail to get correctly, fail to complete all the way, and we'll see why. In general, how can the even property help you? If f is even, again, we're always assuming continuity. If f is even, okay, if f is even and continuous, all right, if f is even and continuous on the closed interval from opposite of a to a, of course, I'm assuming a is positive, all right, then, okay, the integral from opposite of a to a, f of x dx, how can this be rewritten? As twice the integral from 0 to a of f of x dx. Okay. Or you could go negative a to 0, but that tends to be harder. Okay. 2 times the integral 0 to a f of x dx. And that makes it usually easier because we like 0 more than opposite of a usually. All right, questions about that? That's to help you. And in fact, I can ask you a short theory question, and you need to use that property. I often ask these little 2, 3 point theory questions. If this is that, what's that? Well, f is even, da-da-da. But you know what's even better? If f is what? If f is odd, then that can be really beautiful. Example, integral, negative pi to pi, x plus sine of x dx. All right, guess what? F of x is odd. You replace x with its opposite, you end up with the opposite. Right. Now again, you don't have to graph this, but here's the principle. The graph of an odd function is symmetric about the what? The origin. Turns out it looks like this. Here's negative pi, here's pi. Well, looky here. When you have this kind of symmetry, in fact, I don't care what the shape looks like, right? We have continuity, but I don't care what the shape looks like. If we have symmetry about the origin, and if these are opposites, what is your answer going to be? It's going to be 0. Look, whatever this contribution is, this knocks it out. All right? It's a type of war, right? Answer is 0. So what if this is like cosecant to the 11th x? Okay, at this time, you may not know how to integrate it, but wait a minute. Hold on. Oops, not continuous on there. Yeah. How about sine to the 11th x? Sorry. So, integral of sine to the 11th x from here to here. 0. You don't have to know the antiderivative. Hint, if you see an integrand and you really don't know the antiderivative, or you don't think you'll be able to find it, check to see. Is it odd? If it's odd, and if these are opposites, and you have continuity, you're in business. All right. Again, I won't mess with you in the continuity sense.
That'll be, that's your only on the test.
Yeah, that was like 2, 3 points. Yeah, that's right. 0. I might ask why. F is odd. F is odd. Integrand is odd. All right. So what's the general rule? All right. It's even better. Here you just have to work that thing out, right? If f is odd and continuous, okay, on the closed interval from opposite a to a, I'm assuming a is positive. All right. Then this is great. Then the integral from opposite of a to a, f of x dx is what? 0. So we love that. So integral of negative guy to guy, of a guy who's of something that's odd continuous on that interval, 0. Bear in mind, even if these are switched, it's still 0, right? Because the opposite of 0 is 0. All right. Good news. bad news, good news. We have 2 more things to do. You know the bad news. All right. Questions? Questions? What is a problem that not very few, but few students get perfectly? And you really should do this because it's a student learning outcome, right? How do you evaluate a definite integral when you have to do a U sub? And people routinely mess up their notation on these things, and as a result, they often get the wrong answer. But if you're careful, okay, then you should be able to get good notation and the right answer. Okay, and I do great on form. If you mess up the notation, I can mark you off even if you get the right answer. All right, example. What if there's a U sub? And you have to be very careful. All right, watch your notation. Okay, this is number 28 from Sokowski. 0 to 4, x over the square root of x squared plus 9, all dx. All right. I'll show you 2 ways to do this. The first way is more standard. Okay. In the beginning, okay, we think a U sub's going to work. This is not basic, and I don't see a good way of splitting that. You can't split it. All right. So let U equal. Let's let U be an inside guy. We'll make that nicer. And his derivative is basically in there, up to a constant factor. Let U be what? X squared plus 9. So I can make this entire radicand U. I'll make it nicer. We'd like to avoid a double sum. Not wrong, but we prefer one sum. All right, then du is, what's du? 2x, don't forget, dx. Don't forget that. I do mark off on form, forget that. All right, du equals 2x dx. That's differential form, that's standard in America. All right. Well, there's a kill-bill method. You would solve for x dx, that's half du. I actually call that x dx is half du, and that works. All right. I think compensation is one that is very popular. Okay. But there are a couple of things that we have to do. All right. First of all, we are in the process of going from x to u. There's something that has to change. For the first time, we're going to have to change the what? We're going to go to du, right? What are we going to have to change?
The integral.
Right? Yeah, you're right. The limits of integration. Right, okay. The limits of integration. The limits of integration, right? Well, directly we relate this to these 2 limits, right? And we associate an interval with them. Okay. All right. So we need new limits of integration. Okay. By the way, this is not limit as in chapter 2 limit. It's what we call those numbers. Okay. These are new limits of integration. Okay. And they're for u. Okay. They're for u, not x. So remember, the d blah. That blah is the variable that these are related to. Okay, in this case, these are x values, but we're going to need u values later. All right. So if x is 0, what's u? Here's a function, right? U equals x squared plus 9. That's how I get these things. All right. So u is x squared plus 9. U equals 0 squared plus 9. That means u is 9. All right. These are functions, right? If x is 0, u is a number. It's 9. All right. If x is what? 4. U is, well, 4 squared plus 9, that's 25. U is 25. And they go in the corresponding order, okay? Now, folks, sometimes when you find the new limits, sometimes the greater number is here, the lesser number is there. That's okay. They have to correspond, okay? So zero's guy, some people say u of 0 goes here, u of 4 goes here, okay? It's okay if this number's greater. Okay, don't switch the order just because you feel like it. Okay, you have to correspond. All right. That's one thing. Second thing, let's set this up. Let's start by compensating. Okay, so this integral over here, I'll star it. Okay. Okay, this integral, I'm going to set them up. I'm going to set up the compensation. All right, integral, 0 to 4, we're still doing dx. All right, fraction, x over, notice I'm moving them over, x over root x squared plus 9 dx. Right now, I'm just rewriting it. It would be great, though, if I had a what up there in the numerator. Right, a 2, right? Because I want to get du in there. I want to stash u in there, right? How do I pay for the 2? 1/2, which I'll normally put out here. Sometimes it helps in here, but very often we pull them out. Okay. shouldn't be mixing x and u in the same integral. Let's go to u. Ready? Ready? All right, let's go to u. The 1/2 we keep. Integral from? 9 to 25, right. Again, once again, if it turns out this number is greater than that, that's okay. You have to correspond. Okay, you have to correspond. Okay, all this stuff, 2x dx becomes du over what? The square root of u. Okay, and you agree that's an integral entirely in u. As far as you're concerned, I may as well have given you this. Okay, I may as well have given you this. Any questions? By the way, you remember how in 5.2 you went back to x? Do not do that here. Okay, you're just going to mess yourselves up. Like I said, you may as well have been given this. Don't go back to x. Don't look back. All right? Don't look back. Don't go back to x. As far as we're concerned, we're given this. If you try to go back to x, you will routinely mess up your notation and your answer. Okay, so forget him. We're over there. Don't erase this, but as far as we're concerned, we start there. Whole new ballgame. Any questions? At this point, same old, same old. Big deal, different letter. Okay, 1/2 integral 9 to 25. And by the way, for some of you, to remind yourselves, it might even help to do this. If you write u equals 9, u equals 25. Okay, just to remind yourselves. But remember that if you don't have a label, these numbers are assumed to correspond to that variable. And that's one reason why we don't mix variables in the same integral. Because we know what kinds of values we're talking about. They're u values, not x.